This is a video for doing the math involved in choosing a beam design for your structural calculations in Autodesk Revit for your engineering class. You will notice that I am utilizing the same spreadsheet that I utilized in a previous video where we calculated the reaction forces and the moments for different types of beams. For this video, we're going to be doing an example from a distributed load beam, and you'll notice that we're going to have to be doing some different calculations over here on a separate sheet that I made. So if you want to make a separate new sheet, you can just click the plus next to that and go ahead and create the sheet. I'm going to go ahead and just delete this one, and you can go in and label this. If you want to press pause on the video at any time, go in and place your labels, and you're going to need to create both things on both sides here. So you're going to need every aspect of what I have here. So again, if you want to pause the video real quick and go in and make this, we're going to go through a PowerPoint presentation and do several different examples of math for this. So we're going to go to our PowerPoint presentation here, and basically we have ourselves a beam here that has a distributed load, and there's a live load and a dead load placed on it. So it's going to be 790 pounds per linear foot plus 300 pounds per linear foot, and the beam is 18 feet long. So 790 plus 300 is 1,090, and we have 18 feet. So we're going to go back to our beam reactions, and we have 18 feet and 1,090, and it's going to automatically calculate our reaction forces at A sub y and B sub y, and it's going to go ahead and give us our moment. We're going to go back to our moment, bending and shear, and we're going to do some math for the nominal moment. And you'll see we have our design here. If you see in another video that I have where I showed you how to calculate reactions and moments in MD solids, you'll see we have our max shear stress. So this right here is our shear diagram. This is our moment diagram. And we're going to need these two numbers to do some of the math that we're going to do today. So for our bending strength, we're going to take our moment and multiply it by 1.67. So we're going to go back to our spreadsheet here. And one thing we want to do is I'm going to hit equals, and I'm going to go down to beam reactions, and I'm going to tap on moment. And I'm going to come up here to the top, and I'm going to highlight this. I'm going to right click and go to copy, and I'm going to go back over to our moment diagram, and we don't want to keep this verbiage in here because it's just saying that we're taking something off the moment page. I'm just going to go to paste, and I'm going to go times 1.67. That's what we saw on our spreadsheet here, times 1.67, and we're going to hit enter. What's nice about this is that if I had to go back and change our reactions, our length or our load per foot, we're going to automatically get a different number here. Our next number we want to place in our spreadsheet is the yield stress of steel. And yield stress is how much stress something can take before it starts going into a plastic modulus. It's like it's no longer elastic, like it's a yield point. It starts to give at that point. So we need for ourselves 50,000, kips per square inch. So we're going to come back into here. We're going to put in 50,000, and I'm going to hit enter. We're going to go back to our spreadsheet here. Now, when we come back, we're going to need to get into bending strength. And you'll notice that here I have two separate things. There's a nominal bending moment, and then we get into bending strength. We're going to need this number, which was our moment, and a multiplier, which is basically a factor of safety multiplier. And then we take our yield stress, and then we start talking about how much bending strength we're going to allow ourselves to have. So we need to write for ourselves a function that will take our bending strength, our nominal bending moment, times 12 divided by our yield stress. So we will go ahead and hit equals, and we're going to start parentheses, and we are going to take our nominal bending moment times 12 divided by, close parentheses, divided by your yield stress. And we're going to hit enter, and we should get something that looks like 17.7. We're going to go ahead and use that. Now, you're going to notice a chart over here on the side, and we're going to have to go in and find ourselves a plastic modulus number to use. Now, in order to do this, we need to go to structural-drafting-net-expert.com. There's different places you can get this, but this is an excellent website to use. And we're going to go to steel sections over here on the side, and what we want is wide flanged beams. In our first slide we saw, it says choose the lightest wide flange steel section available. That's why we're going in and choosing this website. And then we will go to properties. And if we go back to our spreadsheet here, you can see that we're looking for a plastic modulus number in cubic inches. So we will go back over here. So we had 17.7 was the number that we have. We want the number that's slightly above that. So we are going to come over into plastic modulus, and we had 17.7. Notice that I'm just following this column where you can see my mouse, and we had 17.7. And We're going to start getting down into some lower numbers here as we go. And we had 17.7 here, 17.4. Right above that is 20.1. We are going to choose a 12 by 16 wide flange beam, and you can see that that would wind up working. So we're going to go into shear strength now, where we're going to take one of our reaction forces and we're going to multiply it by 1.5. So let's go back to our spreadsheet here. So our shear strength limit is what we're going to look at here. So I'm going to go ahead and say equals. And what we want to do is we want to come over to our beam reactions, and I'm going to come up here and I want to just copy this up here. I'm just going to right click and go to copy, and I'm going to go back to my moment diagram, and I'm going to highlight this, and I'm just going to go ahead and paste that. I'm going to right click and go to paste, and we're going to go to times. Remember, this is a kind of a factor of safety calculation, times 1.5. So I'm going to say 1.5 and hit enter. There's going to be our shear strength limit. We go back to our calculation here. We go down here to shear strength, and we're trying to find out if from the information we just gathered, if whether or not this is going to be a doable beam. We want to make sure that we cover all of our bases as far as the area of the beam, the dimensions of the beam, and also the thickness of the beam, of whether or not that's going to work. And we're going to have to get some data to place into this equation. So we're going to have to go back to our website here, and we have 12 by 16. We're going to go to dimensions, and in 12 by 16, if we have to scroll down again, scroll all the way down to the bottom and try to find that 12 by 16 beam. We had to scroll for a little bit here. There it is right there, 12 by 16. We have, for our dimensions here, which we can get into a diagram in a minute and take a look at what these numbers actually mean. But here's the area of the beam, the cross-sectional area. These are your dimensions, and then this is the thickness number. So when we go back to our spreadsheet, we're going to need to take some of these numbers and place them over here. So for our F sub Y in our calculations, if we go back to here, you're going to notice that it went ahead and stuck with the 50,000 for yield stress. For F sub Y, we're going to go ahead and hit equals, and we're going to come back over and just tap on our 50,000. Let's just go ahead and place that there. Now for our dimension values, we want to go back to our spreadsheet here, and you will see for D, they are taking 11.99 right in here. So it's the exact same thing that we see here. We see 12 by 16, we see 11.99. We're just going to come over and make this a little bit easier. You could just put in these numbers, but I like to give myself a little bit of a separate area to place these numbers over here on the side. It makes things a little bit easier as we go. And then for our thickness number, we have 0.22. I'll come over here, 0.22, and hit enter. Let's go back to our shear strength calculation. 0.6 times 50,000 times 11.99 times 0.2. So I'm just going to come back into here. I'm going to hit equals again, 0.6 times yield stress times our dimensional value times our thickness, and hit enter. We come out to 79,134. It's the exact same thing here. Now we're trying to make sure that obviously that number is above this number, so it does work. So we can stay with this value. Now, as we scroll through, when you talk about what these numbers mean, when we look at this plastic section modulus, TW is the thickness of the I-beam, D is kind of, your depth as far as height goes, and X is the width right in here. So we can get more and more into different types of axis lines that we have, and, X is actually the X-axis, excuse me, and you have the Y-axis. We can get more into the other dimensions up here at the top as we go on, but kind of give you an idea of what you're going to see as we go through when you're talking about sizing a beam. So now we're going to go to check deflections next. So we have our dead load and live load deflection limit and just our live load deflection limit. So our live load that we said earlier in the value, the live load we had earlier in this was, let's scroll back up here. Let's take a look again. Our live load is 790 pounds per linear foot. Dead load is 300. So live load is 790. Dead load was 300. One thing I forgot to put in here was the I for inertia from our values from the properties over here. So as we go through, you can see when I come down to 12 by 16 again, I'm going to scroll down here. You might have been asking, why is that one box absent there? I just kind of left it. We have 12 by 16 here. I'm going to put in 2.82 for the I up here. So let's put in 2.82. I'm going to hit enter. Now the length of our beam was 18 feet. We'll get into what the modulus of elasticity of the beam is here in a second. So I'm going to come back down here to our limits here, And we have 18 times 12 divided by 240. So what I'm going to do here is I'm going to go equals, and I'm going to go 8. I'm going to just come over and tap 18 times 12 divided by 240. And that is inches. So that is, just 0.9 inches, so just barely underneath 1 inch is your amount of deflection for this beam we're working on. Now for just the live load limit, if we come back to here, we have 18 times 12 divided by 360. Now up here, I don't really want to mess with this. I just want to, right click and go to copy. I'm just going to come back down into here. Just going to double click. I'm going to go to paste, and I'm just going to put in 360. I don't feel like writing that out again. I'm just going to go ahead and hit enter. We now have our deflection limits about whether or not we can have a beam. And if it goes, under that, we have to come back and redesign. So let's go back to our calculations here. We're going to go ahead and take the beam that we have, and what we got to do now is we have to multiply, we'll do some, some math in here to try to decide whether or not our beam meets these deflection limits. So this can get pretty interesting as we go through, as we're going to have to do a lot of functions, and we're going to have to do a lot of parentheses work. But through everything we do, we're going to get there. So I'm just going to go ahead and hit equals, and I'm going to start a parentheses, and I'm going to say 5 times, and I'm going to do parentheses. We're going to come back into here. Now our deflection, our reaction force was 1,090, if I remember correctly. So if I come over here, that was not it. It was our reaction, our other value we had was not this. Our 1,090, let's look back into here real quick. Our 1,090 was our total amount of weight together. I was thinking about reaction force as a total amount of weight. So it's 790 plus 300. So one thing I can do is I'm going to go ahead and just do 2 parentheses, and I'm going to say 790 plus 300. I'm going to close my parentheses here. I'm going to come back to our slide here, and I'm going to go divided by 12. I'm going to say divided by 12. I'm going to close those parentheses, and I'm going to say times again. And we're going to go back to our slide, times, and this is going to be 18 times 12 to the 4th power. So we're going to have to do 2 parentheses, and it's going to be our distance here. So our 18 is actually going to be F10, so it's not letting me see that. F10 times 12, so let's come back down here again, F10 times 12, close parentheses, shift 6 to the 4th power, close parentheses twice, divided by, let's go back into here, 384 times 29,000. So one thing I failed to do is down here where it says E, that's going to be 29,000, and this will make sense once I go in and place it. So I'm going to say 384 times, and I'm going to say F11, Let's go ahead and capitalize that. I'm going to go F11 times, we're going to go back to our slide, 103, and it says 1216 for the I was 103. I can go back up and change this here in a minute. I put in the wrong number accidentally. So we're going to go to F7 times F7. Close your parentheses. Should be able to close our parentheses from here. I don't want that to be closed parentheses right there. I want that to be black. So I need to come back into here, get rid of that. I said times here, and this should work. I need to put, I didn't start parentheses over here. That's what I didn't do. That's what I failed to do at the beginning. This is what I just need to do over here on this side, and I should be able to hit enter. Now it's not going to give us a number right here because I don't have 29 million. So right here, 29 million, and this one up here has to be 103. And we have 0.86 is what we came out with. I'll come back and explain what the 103 was here in a second. I accidentally put in the wrong number. Apologize for that. But we have our actual numbers in here, and we found our deflection limit. And it's not going to work because, it's not within the boundaries that we set up here. So what we actually need to do is go ahead and find a different beam. So as we go through, remember what yield stress is that yield point is where it all of a sudden starts to change. Modulus of elasticity is something that how much it can take for it to return to its normal behavior. So when we went through, we just checked our deflections. We need to go in and actually look for something else. So it says 12 to 16 is not going to work. So we need to go back and see if 12 by 19 would work. So what we're going to do is we're going to look for this x-axis value right here. We have 130 here in this case. So we had 103. Let's go back and see if a 12 by 19 would be better. and we go back to 12 by 19, we go back to 12 by 19, scroll down to here, 12 by 19, I went past it, 12 by 19, these are our dimension values. Let's go back up to our properties. Now let's go down to 12 by 19 this time instead. So I'm going to scroll down. We're going to find 12 by 19. 12 by 19. Yeah, this was I accidentally came over to this. I apologize. I was on the y-axis instead of the x-axis. That's just in making a video. I made a quick mistake. The 103 now, if we go up to 19, will that work? So let's go a little bit wider of a beam, a little bit, a little bit greater amount of area, just a little bit. And this is going to be obviously out into a 130. It's going to beef it up a little bit. So if we go back to here and I go to 130, our value changes. And we're going to say, yes, we're going to go ahead and accept that. So as far as going through and doing the math for your beams, the best part about creating any one of these spreadsheets is that you can actually come in here and change the numbers and automatically everything's going to adjust. Now, linking things from a beam reaction force spreadsheet that we made earlier can make things easier, because what we can do is we can change the beam length. You can change the amount here. So like if I come in and I say, I just want to change these values to, let's say, 20, I can come back over and some of the numbers are going to change. You're still going to have to go to your spreadsheet here on this website and plug in the numbers to see if things actually work or not. You're still going to have to do that. In some of these, it's not automatically going to change, these values, but a lot of your calculations over here on the left are going to automatically change because you're basing your numbers off of the beam length, the load per foot, and then taking your reaction in your moment for some of those calculations. So this has been a video on how to go about calculating, nominal moment, bending strength, deflections, and choosing whether or not the deflection amount meets your load requirements for your design in Autodesk Revit, or excuse me, in Microsoft Excel for your civil engineering class.